Hi. So previously we saw convolution in continuous time as well as in discrete time, and we also saw the impulse response function of a particular system, which is, let's say, in the continuous time I write it as h of t. So the impulse response h of t allows us to show the output y of t with respect to any particular input x of t. So if you have your x of t, give it to the system and you get your output y of t, the impulse response h of t allows us to predict or to compute the output y of t as x of t convolved with h of t. The same thing happens for the discrete time case. Y of n is x of n convolved with h of n. So we saw that the impulse response completely characterizes the response of a linear time invariant system. So now we will see some of the properties of systems and some properties of convolution itself. So these topics are from the textbook, Oppenheim's section 2.3. First, we will see what is the commutative property of convolution, which essentially is x of n convolved with h of n is equal to h of n convolved with x of n. Essentially what it means is, in this figure, the order doesn't matter. If you put your x of t here and your h of t here, you will still get the same y of t. Okay, so this can be so if you write the convolution sum, y of n is, this is the form which we have seen earlier, x of k h of n minus k. This is equal to, by this property, this is equal to h of k x of n minus k. So essentially what is happening here is, in the form which we saw it earlier, if you see the convolution operation, we flip and shift the h of n. So due to the commutative property, we can also flip and shift x of n. So essentially what this means is, based on the output which you're trying to determine, it may be sometimes easier to flip h of n, or it may be easier sometimes to flip x of n. So based on what is easier for you to compute, especially while you're computing by hand, you can use this property to determine which of them you want to flip. Okay, so the proof of this is very simple. You can just do it by a change of variable. So if you just replace n minus k as m, and then you find out the value of k in terms of the new variable m, and also find out the two limits, k goes from minus infinity to plus infinity. So if you get the new limits for m, that also you will get as m equal to infinity and m equal to minus infinity. Essentially, with that change of variable, you will get the desired result. That is, y of n is same as h of n convolved with x of n. Okay. The same thing applies for the continuous time case as well. Again, this is again, the proof is again by a simple change of variable. Okay, so I urge you to just try it out yourself. Okay, so y of t is h of t convolved with x of t, which is also same as x of t convolved with h of t. So that was the commutative property. The next property is distributive property of convolution. So this property states that convolution distributes over addition. Convolution distributes over addition. So x of n convolved with h1 of n plus h2 of n is equal to x of n convolved with h1 of n plus x of n convolved with h2 of n. So this, the convolution, if you open up the bracket, this convolution distributes over addition. Okay. So essentially what this means is, if suppose you have a system like this, x of t convolved with h1 of t plus h2 of t, then so this is represented by this block diagram. There is the whole system here is represented by h1 of t plus h2 of t. That is what is shown here. X of t is convolved with this, and you get a y of t. This y of t is same as, if you open up the bracket, x of t convolved with h1 of t convolved with h2 of t, and then added together, you get the same y of t. So this y of t and this y of t are the same. Okay, so convolution distributes over addition. This may be useful in certain cases. This property can be used to simplify complicated convolution expressions if you are able to split it into two constituent parts. Okay, again, this will be useful in solving problems.